So everyone, I want to do an example from the book, and I'll work my way through page 158. This is Stewart, edition 5. All right. And it says the position of a particle is given by the equation S equals f of t equals t cubed minus 6t squared plus 9t. Let's be clear for you guys who haven't had physics. S is position. Okay. All right. V is velocity. Sometimes they use S as speed, but usually it's velocity has a vector. Speed does not. Usually speed is just V without the arrow over it. Everyone, this is position. And then it gives you some things like where T is measured in seconds and S is in meters. All right. So I know that this would be meters right in the Y, and this would be time in seconds. Everybody with me? And I would call this S, the axis S or Y, right? Because it's S equals some T's. And everybody, unless you're Superman, and you guys are not, and neither am I, we can't make time go negative. So when I look at this, I don't worry about putting -1 in this function. Is everybody with me? I just look at this and say, hey, first of all, that sure looks factorable to me. And I would do that. And then it happens again. Oh, lo and behold, it's a book problem. And does everybody agree that that function factors the t times the quantity t minus 3, which that means at time 0, it's at the origin. It's at position 0. And then 3 seconds later, it's at 0 again. That is its position. I don't know what this stupid particle is doing in between. Maybe we'll find out. Everybody, because of the intermediate value theorem, I know it either does this or this, not both. I guarantee because of the intermediate value theorem, it does not do this. Because I would have found this 0. Is everybody with me? It can't go positive negative without going through another 0. So I try 1, and I see that the result is positive. I don't particularly care how high it goes. I'm not scaling this. But right now I know it goes like this. And then I try another time. After 3, like 4. 4 times 1 squared is positive. So it doesn't do this. And I know now it kisses the axis and goes like this. Because what is the mother function of this? The mother function of this is y equals x cubed, which we know looks like this. So while we don't know what this is doing around the origin, the second part of stuff, you know, the 6x squared minus plus 9x, we know that at the extreme it's got to do this because it's y equals t cubed. So that's the graph. By the way, I don't think it even asks us to graph it, all right? It doesn't even ask us, but we're going to use the graph to kind of understand. So, boom, we got this all going on. All right, we got this all going on. And now we got that this thing factors, and there it is. Boom, awesome. And it says find the velocity at time t. All right, what you have to understand right now is that you have a function that gives you meters at a certain time t. Everybody, you came to school this morning at exactly 54 miles per hour because I know none of you speed because you're all good human beings. Yeah, okay. I might have come to work at 59 because I know the police officers won't pull over an old man doing 59. Everybody, what you have to realize is that when it asks for velocity at a given time, that is, again, not an average rate of change, but an instantaneous rate of change, where the slope in units is meters per second, right? So the second it asks me to find the velocity at time t, for letter A, guys, it's asking you to find the derivative of s. So I have s of t, and I'm going to write this out. I have s of t equals t cubed minus 6t squared plus 9t. All right? If I take the derivative, s prime, right? And this is the hard part for students. The derivative of a position function gives me velocity. And that is 3t squared going to run out of room. 3t squared let's get this over here, minus 12t plus 9. Everybody, that is the velocity function at time t. So guys, what's my position at time 0 is 0. Does everybody see? If I plug 0 into the black function, I got 0 for position. What's my initial velocity at time 0? Nine meters per second. Guys, I plug 0 into that blue function. It's 9 meters per second. So while this particle was at the origin initially, it was, when time started, it was flying off. Okay, some event happened, and this thing had velocity. All right? I don't particularly care about the event in calculus. Typically, that's really important in science. All right? But there it is. That is letter A. We are done. Check it. All right? Letter B says, what is the velocity after 2 seconds, after 4 seconds? All right. Everybody, I would guess the velocity at 2 seconds is probably negative. I will guess the velocity after 4 seconds is probably positive. But that's a guess based on a really horrible graph. And why bother with that? We can go for B. I want V of 2, and I want V of 4. I literally just plug 2 in here, guys. I get 12 minus 24, negative 12 plus 9. I get negative 3 meters per second. That makes sense to me. I plug in 4, I get 48 minus 4, I get 9 again. And I know that I probably did that faster than you, but that's all right. Everybody, a lot of times students say, Anderson, it can't possibly be negative 3. Look at your graph. Negative 3 is down here at 2. Guys, that's not what this graph was, a position. The red curve is position, not a velocity. To look at the negative 3, you have to be looking at this slope of line. That slope of line at 2 is negative. Okay? There's letter B. Awesome. And that should make sense to you. Guys, the particle shoots off at positive 9. It's going away. And then it comes to here, and the velocity stops and it's 0. Then it heads backwards. You put the car in reverse and go back to position 0. Then you throw the car and drive again. And you go forward. That's what this particle did. All right. When is the particle at rest? Well, I can take some guesses. 2.5.
What is this?
That's 3. Okay, 1.5, and somewhere else, actually. Yeah, where is it at rest? What does that mean? 3. Guys, when a particle is at rest, velocity is 0. Huh. Now, I know this is a book problem because I come back up to this beautiful thing. And what do you notice immediately? Hit factors. Let's pull the 3 out, see what we get. All right, let's pull the 3 out, see what we get. I get the velocity function equals 3 times t squared minus 4t plus 3. Oh, I love trinomials. How about t minus 3 and t minus 1? So everybody, when is this equal to 0? V of t equals 0 at time equals 1 and 3. So everybody, my graph is really crappy. My graph is crappy. This 0 point that I had at 1.5, Justice, that you called out right, should be over at 1. I did get 3 right? Change from going backwards to forwards. All right. So everyone, I want to be clear about this. At time 1, the particle was going forward. And then after time 1, the particle is going backwards. And then it's going forwards. Okay? And it goes forward from then after. Maybe it's a neutron. And it bounced off something. I have no idea, but it shot off after time 3. So t is 1 and 3. Whew! We've done ABC. We've done ABC. Group it all. I don't know why. I have a tendency to do this, guys. I don't know why I just don't erase, but I feel like after all that precious work, we just want to keep it. So we'll put it up there and go back up to the problem. When is the particle moving forward? That is in the positive direction. So guys, they're not asking about position. They're saying, when's the particle moving forward? Well, I want to be clear about this now, and I'm going to do this through a velocity graph. Did you guys catch that this was the factored, this is S prime, this was the factored velocity graph. So I'm going to forget the position graph up here, and I'm now going to graph velocity versus time. And everyone, these units are different. This is meters per second. This is seconds. At time 0, we had already figured out that it was 9. At time 1, we figured out it was 0. And time 3, we figured out it was 0. So everybody, I don't know if you caught this then. All right. But it's moving down. And at time 2, if you plug 2 in here, does everybody see it becomes negative? You get a positive 1 here on the on this first one. Whoops, there. You get a positive 1 here, and you get a negative 1 here, and that makes the whole result negative. So again, intermediate value theorem, guys. This was a polynomial. That's the graph. That is the graph of the velocity. So when is the particle moving forward? That is in the positive direction. Guys, this is tough to understand. When we look at the graph here, I want you to see that the velocity is positive here. The velocity is positive here. This is like driving your car dry. Your speedometer reads positive. And then all of a sudden, you drop your car in reverse in here. And your car goes backwards. By the way, your speedometer still reads a positive number. Because when you put the car in reverse, that's like a negative action. But we'll talk about that later. So everybody, for letter D, when is the particle moving forward? How about when time is 0 to 1 and 3 to infinity? That's when it's moving forward. Everybody, when's it going backwards? When's it going in the negative direction? Between 1 and 3, right? What's it doing at 1 and 3? Velocity is 0. It's at rest. Guys, it's not going positive or negative. It's 0. All right? It is 0. So that's letter D. Draw a figure to represent the motion of the particle. And then find the total distance traveled during the first 5 seconds. All right. We're going to keep all this. Here we go. We're going to keep all this. And this is tough. All right. I'm going to keep this because we're going to need these graphs. I'll put it over here. There it fits inside. Perfect. All right. At time 0, we plug that into the original function up here. Okay, everybody? At time 0. And we know the position was 0. All right, so everybody, there I am. We happen to also know that for the first second, right, from our velocity graph, it's going forward. So I'm going to check t equals 1. And I'm going to put that in the position function up here, and I'm going to plug in 1. 1 minus 6, negative 5 plus 9. How about position 4? So my particle does this for the first second. They'll change colors. But everybody, what happens at time 1? It goes to 0, and then this particle swings a U-turn right here in the negative velocity. And it goes backwards for how long? Until time equals 3. It goes backwards until the next 0 on velocity. So while this is pretty interesting, I don't care about time 2, time 2.5, time 1.5. I really only care about S of time equals 3, the next 0 on velocity. And when I put S of 3 in, and we've already done this one, when I put 3 up here, I get position 0. So this particle comes all the way back. And then what's it do? Well, from the velocity graph, right, it turns from negative 5. That sucker swings a U-turn and heads off into the sunset. Right? It gets bigger and bigger and bigger. It never hits another 0. Everybody, it asked me to do it, the time equals, that's the diagram, but then it asked me in the next one, find the total distance of the particle traveled in the first 5 seconds. To finish this diagram on letter E to help us, letter E to help us, I'm going to do T of 5 in purple, just so we have it out here, T of 5. I'm going to put that in the position function, S of 5. Put in 5, 125, minus 6 times 25 is 150. That's negative 25 plus 45. I get the position as 20. So it just keeps going. And at 5, it's at position 20, but then it just goes on too. So there's the diagram. And this is how the book diagrams it. Everybody, you'd get the same thing from this graph. Is everybody with me? This is the same graph, but this is just a diagram of how it goes forward and backwards. Because everybody, if the next question is big, I will tell you that the total distance traveled by the particle for the first 5 seconds is not 20. That's its position. All right? We got to pretend to be the particle here. All right? And if I stand on my floor at time 0, I'm here at 0. I turn for a second and I travel for 4. I turn around, I travel back 4. Guys, at time 3, I've traveled 8. Is everybody with me? 4 out, and again, if I do this in marker here, 4 out, 4 back. And then what do I do? From time 3 to 5, I travel out 20. Well, everybody, you have to pick these distances up in purple here. So it's 4, 4, and 20. Everybody, the distance this particle traveled in the first 5 seconds is 28 meters. What's its position at time 5? 20 meters. But this sucker went forward and then backwards before it went forward again. All right? And everybody, we have just used a polynomial function that describes the position of a particle way back up here to not only find the velocity, all right, but its position and its distance. Everybody, does anybody know what the rate of change of velocity is called if you've been in physics? The rate of change of distance the rate of change with respect to distance of time is velocity. The rate of change of velocity with respect to time is acceleration. All right? So everybody, we're going to actually get another derivative eventually. We're going to look at this velocity curve. All right, if I bring this down, we're going to look at this velocity curve. And I tell you what, the one thing I should be able to pick out is I'm pretty sure I know when the acceleration is 0. Because that's the derivative of the velocity curve. Everybody, I know that the acceleration is 0 at 2. The irony here is this is a positive velocity, but I will tell you that we are slowing down. So it's a negative acceleration. All right, and we'll work on that. And again, this is really difficult initially. Because what it is sometimes you're looking at the value of the curve, and sometimes you're looking at the tangent line at an instant on the curve. And it's the same graph. So while I can tell you at time 0.5, the velocity is positive, because there's the value, I will tell you that the derivative of that is negative. All right? All right, everybody. That's enough for today. 18 minutes. Ooh, that's painful. I hope you watched it all.